Okay, hello everybody, and thank you very much for joining us in today's webinar. We are excited to have you here and look forward to diving into techniques and best practices for improving your microplate reader experiments together with you. My name is Anne-Catherine, and just like my colleague Martin,
Oh,
I'm an application specialist working for BMG LabTech. Together, we have the pleasure of guiding you through a set of experimental data featuring various optimization strategies for different measurements on microplate readers. One important note in advance, you are of course very welcome to ask questions at any time. For this, please use the Q&A tool of this platform. Here you can enter your questions in written form at any time during the presentation. You also have the opportunity to vote up existing questions of other attendees in case you think they are very important or if you are about to maybe type in the same question. We will then address the questions after the presentation part of this webinar. Having this said, I will now move on to a brief overview of BMG LabTech and our portfolio, just in case you haven't heard of us yet. We are a microplate reader manufacturer, but the special thing about us is that we are solely focused on microplate readers. In the meantime, we gained more than 30 years of experience in the field. And through the years, we have managed very well to bundle relevant knowledge within the company, as we have very low fluctuation in our staff. In fact, more than 30% of our staff have been with the company for more than 15 years. In the meantime, we are represented in the 5-digit range in scientific publications in peer-reviewed journals. And based on these facts, it is hardly surprising that we were rated with 4.7 out of 5 by our customers in an independent online platform. We are providing microplate readers of various types, ranging from single-mode to multi-mode instruments, from low-budget ELISA readers to high-throughput devices. Accompanying our main products, we also sell various microplate reader accessories, like our atmospheric control unit or stackers that provide customers with true walkaway solutions for medium to high throughput needs. And we even offer all of this made in Germany. On top, our reader control software and the data analysis software are all developed in-house. On this picture, you can see our headquarters in Germany with the beautiful castle of Ottenberg in the background. And at this place, our microplate readers are not only conceived and developed, but also assembled and tested. Our readers are manufactured in Germany, but they are of course sold worldwide. To this end, we have built up a global network with 5 subsidiaries in Australia, Japan, in France, UK, and the US. And we are presented through our distributors in over 50 countries worldwide. Our portfolio ranges from monochromata-based readers like the Vantastar, which is a very compact and user-friendly device, or the very flexible and sensitive Clariostar, which is of great support, especially in assay development, up to high-end devices like the Ferrastar FSX, which is our flagship reader. The Ferrastar provides very fast and most sensitive measurements for high throughput applications. For customers with very clearly defined needs, we also offer dedicated single-mode devices like the absorbance-based SpectraStar Nano. Further, the Omega series represents an entry-level filter-based platform for all needs. And finally, the Nephelostar, our exotic, uses a light scattering-based technology to measure solubility or microbial growth. But now let's move on to the goal of today's webinar, which is, of course, improving your measurements on the microplate reader. We will provide you with some tips and food for thought to improve your microplate reader measurements. We have divided this into 2 sections. We will start with everything that has to be considered before the measurement and the setup of the assay, like, for example, the microplate color, the wavelength, and the bandwidth. And in the second part, everything that can or maybe should be adjusted when setting up the protocol or while measuring at the microplate reader, like focal height, different scan options, gain, flash number, and integration time will be dealt with. Let's start with the decisions that have to be made in advance. One question that we are frequently asked is which microplate color delivers best results? And of course, there is no general answer to this question, as every plate color has its justification. The ideal plate color depends on the used detection modes. We will first have a closer look at absorbance measurements, which are, for instance, used to evaluate ELISAs, to quantify protein concentrations, or also to quantify nucleic acids. Since absorbance measures the transmission of light through a sample, it is self-explanatory that the microplate must be transparent for this type of measurement. But even within transparent plates, there are some differences. While regular plates made out of polystyrene are only transparent down to about 300 nanometers, other plates, for example, those made out of cycloolefin, also allow light below 300 nanometers to pass through the plate. This may be completely irrelevant for most measurements, but DNA, for example, is measured at 260 nanometers, and dye-free protein measurements are carried out at 280 nanometers. Here, the use of UV transparent plates is essential. In the graph here on the right, the absorbance of DNA samples in either polystyrene plate, here shown in blue, or cycloolefin plates, here displayed in green, is shown. And as you can see, the background absorbance of polystyrene plates completely masks the absorbance of DNA, which should show a clear peak at 260 nanometers. This peak is visible when evaluated in cycloolefin plates, here shown in green. So here, the use of cycloolefin plates is definitely indicated. Especially for absorbance measurements, the plate's influence on meniscus formation also plays an important role. To understand the influence of meniscus formation on absorbance measurements, we will first need to take a look at the path length of a sample and its role in the calculation of the sample's concentration. I guess most of you know that there are some compounds out there that show natural absorbance. We have just looked at one example, the DNA. If the respective extinction coefficient of a compound is known, you can calculate the concentration of the compound directly from the absorbance values. In this calculation, the path length plays an important role, as you can see in the equation below here on the slide. Path length means the height of the liquid column through which the light must pass during the absorbance measurement. If you measure the same sample with 200 microliters per well instead of 100 microliters per well, which results in a double path length, you will also double the absorbance value, as shown in the upper right graph here on this slide. In bigger volumes, the light has to travel through longer path lengths and will meet more of the absorbing compound, resulting in higher absorbance values in the end. If we do not correct for the different path lengths, we obtain different concentrations for what is actually the same sample of identical concentration. We will get back to this in a moment. But first, having this in mind, we can have a look at a special case of path length variation due to meniscus formation. A meniscus is a manifestation of a capillary action by which either surface adhesion pulls a liquid up to form a concave meniscus, as shown in the schematic at the bottom of the slide here, or internal cohesion pulls the liquid down to form a convex meniscus, which only plays a minor role in microplate reader measurements. Nevertheless, when a meniscus is formed, the path length is changed substantially. Hydrophilic surfaces, such as tissue culture-treated materials, are more likely to lead to meniscus formation than hydrophobic surfaces. For this graph here on the upper right, water was determined in different plate types. The same volume of water was, of course, used in all cases. And as you can see, tissue culture plates lead to a clear meniscus formation, while hydrophobic plates, like for example a cell suspension plate, don't. So you should therefore always be aware of the surface treatment of your microplate and how it may influence the meniscus. Only use surface treated plates when you really need their characteristics, and also try to avoid agents like tris or detergents in general. We are, of course, aware that sometimes it is impossible to eliminate such agents and that there is no alternative to a specific plate in some setups. For these cases, we offer the automatic path length correction. For the correction, the reader automatically measures additional wavelengths of your sample without additional time expenditure, and from this information then calculates the path length of each individual sample. So at the same time, it compensates for meniscus effects and also for well-to-well variation caused by differences, for example, in the pipetting or something like that. And if this correction function is used, you can again see in the lower graph here on the right side that you actually now get the same absorbance values and the same concentrations for the same sample, also when measured with different path lengths. Okay, so much for the absorbance measurements. But when it comes to fluorescence measurements, things look quite different. Here, no light has to pass through the sample. Excited fluorophores emit light into all directions, so the emission signal can be detected also from the same side of the plate from which the excitation light came from. A big hurdle in fluorescence measurements is, however, the unspecific excitation of background components. This background can dramatically reduce the signal-to-blank ratio of the measurement. Black plates are recommended here for fluorescence measurements as they partially absorb light and quench the signal. Here in this graph, signal intensities of fluorophore standard curves were measured in plates of different color. Here, white plates lead to a substantial increase of the background as they amplify the present signal. But a higher signal is of course not bad in itself. To see the actual effect, you have to look at the signal-to-blank ratio. Signal-to-blank shows the ratio of a specific signal of your assay divided by a background signal. So it gives you an idea of the dynamic window of your assay. So higher values are of course desirable here. And as you can see in the lower graph, black plates lead to a maximum signal-to-blank ratio, since they reduce the background. They are followed by black plates with clear bottom and clear plates. Okay, luminescence, on the other hand, inherently shows a low background signal, as there's no excitation event needed and unspecific components are not that easily excited. However, luminescence emission shows a lower signal compared to fluorescence emission. Therefore, the amplification effect of white plates that we were just talking about is actually beneficial in this detection mode. As shown here, the weak signal is maximized when measured in white plates, followed by white plates with clear button, and clear plates and black plates actually show no signal amplification effect at all. The result is also reflected in the signal-to-blank ratio, which is highest in white plates and lowest in black plates. It also has to be mentioned that there are gray plates available on the market. Next to the signal amplification, those plates additionally reduce the well-to-well crosstalk. And with this, I will hand it over to Martin, who will provide you with some insights on bandwidth and wavelength selection.
Thank you, Anne. So, Yeah, I would like to start with the different optical settings that can be adjusted to optimize your microplate reader measurements. First up, we have the selection of wavelengths. Each measurable light signal has a specific wavelength range for emission and/or excitation. In the graph on the upper right, you can see the excitation and emission spectra of a fluorophore. As you can see, both excitation and emission curves have a peak at which relative intensities are at a maximum. Excitation and emission wavelengths on a microplate reader should be chosen close to these maxima to improve the signal output and overall limit of detection. In this case, we selected a wavelength of 480 nanometers for excitation and a wavelength of 530 nanometers for emission. Importantly, excitation and emission wavelengths should be selected so that they have a difference of at least 30 nanometers in order to prevent signal bleed through from excitation to emission channels. In the graph below, we now plotted the detectable fluorophore concentrations versus the excitation wavelength. As you can see, choosing an excitation wavelength near the excitation peak, in this case 480 nanometers, resulted in the lowest and with this best limit of detection. Whereas increasing the or moving away from the optimum excitation wavelength decreased the limit of detection significantly. At this point, it is also important to remember that you don't measure at one distinct wavelength, but rather a wavelength range, which is defined by the bandwidth. For example, an emission wavelength setting of 450 nanometers with a bandwidth of 10 nanometers will result in a measurement in the range of 445 nanometers to 455 nanometers. Depending on your assay, it can be beneficial to use narrower or larger bandwidths for your measurement. For fluorescence-based measurements, generally it is better to select a narrow wavelength bandwidths for the excitation part of the measurement, whereas emission wavelengths can be set a little bit broader to increase the measured signal. We see the effect of the excitation bandwidth in the figure on the upper right. So as you can see, we also here have an optimum. In this case, the lowest limit of detection was achieved with bandwidths ranging from 12 to 20 nanometers, whereas going beyond that decreased the limit of detection significantly. For luminescence-based measurements, the picture is looking a little bit different. Here, usually larger bandwidths are beneficial. This can be seen in the figure below. As you can see here, with increasing bandwidths, we have also an increase in the signal to background ratio. However, it is important to note that depending on the luminophore, there's also optimum, and if you go above this, the limit or the signal to blank ratio can decrease. So in this case, we have the optimal signal at a bandwidth of 60 nanometers and a decrease when going above that with 80 nanometers. Choosing bandwidths that are larger than the optimum can accordingly result in a drop of signal to blank. Another point to consider in regard of the wavelength and bandwidth is the choice between filters and monochromators. Filters offer, in general, higher sensitivity in comparison to monochromators, but are also limited to only one specific wavelength and bandwidth. This increased sensitivity is beneficial when performing assays near the limit of detection. While filters might be more sensitive, the monochromator offers a huge flexibility by allowing manual selection of excitation and emission wavelengths and bandwidths. But ideally, you would like to have both. For this purpose, BMG LabTech developed our patented LVF monochromators, which combine the full flexibility of a monochromator with filter-like performance. So as you can see in the graph below, we have at close to 3.5 times more light passing through the LVF monochromator in comparison to conventional monochromators, offering you both flexibility as well as sensitivity in your assays. While in many cases it is sufficient to select wavelengths and bandwidths based on a signal molecule, some assay systems, as Anne mentioned this earlier, in case of autofluorescence, can have a high background signal that needs further adjustments. One such example that specifically impacts fluorescence is the autofluorescence. Autofluorescence is caused by fluorescent assay components, usually in the green to blue spectral range, which can be seen in the graph on the left, that interfere with the actual fluorescence measurements. This often occurs in cell-based measurements, as highlighted in the right graph, as many cellular as well as cell culture media components fluoresce, for example, media containing phenol red. So how to reduce autofluorescence? In order to first highlight this problem, we compared different assay solutions regarding their impact on the signal to blank ratio. This is highlighted in the graph to the upper right. If the background noise is high, this will result in small signal to blank ratios, as is indicated by the column to the very right, which is medium containing phenol red and FBS. Specifically in cell-based applications, alternatives to regular autofluorescent media, such as phenol red-free media or serum-free media, these are the middle columns, or even PBS should be used. As you can see, this can lead to significant improvement of signal to background ratios with the highest achieved here by using PBS plus buffer. Also worth considering could be to switch to a redshifted dye. This is highlighted in the figure to the lower right. Since autofluorescence mainly concentrates to the blue to green wavelength range, using red shifted dyes instead of green ones can improve signal to blank ratios significantly. And with this slide, I would like to conclude the considerations that should be taken in regard of wavelength and bandwidth selection. And with that, I hand over to Anne again, who will cover further adjustments that can be made in the measurement protocol.
Okay, thank you very much for these insights, Martin. And yeah, talking about potential options to reduce negative effects of autofluorescence, the use of bottom optics is also a good idea in some scenarios. Let's have a look. When working with BMG LabTech readers, this is actually nothing that has to be decided long in advance before you start your measurement. The switch from top to bottom optics can actually be done with just one click in the software. What you, however, need to think about in advance is which plate you're going to use for your measurements. Similar to absorbance assays, light has to travel through the bottom of the plate when using the bottom optic. Therefore, you again have to use plates with transparent bottom. Bottom optics should be used especially when your target is located at the well bottom and you have unspecific fluorescence in the supernatant of your sample. This is especially the case for cell-based assays with adherent cells and cell culture medium, including serum and phenol red. In this example here on the right side, you can see the signal to blank ratio of red fluorescent cells that have been measured in different media with top and bottom optics. For this, PBS with known low autofluorescence was used next to medium with serum, but without phenol red, and medium with both serum and phenol red. Measurements with the top optic are shown in red, while measurements done with the bottom optic are shown in pink here. And as you can clearly see, especially when serum and phenol red are present in the supernatant, the use of bottom optics leads to a substantially higher signal to blank ratio compared to the top optics. Okay, so much for the decisions that have to be made in advance. Let's move on to the basic parameters that have to be adjusted in the control software when measuring with the reader. And one of them is the focal height. Focal height is defined as the distance between the detection system and the microplate. This parameter is not only relevant for assays where the signal is concentrated to the well bottom, as those adherent cells we were just talking about. In most assays, the target fluorophore is distributed homogeneously in the liquid. Nevertheless, the obtained signal intensity is not the same in all the planes. Usually, the ideal focal height can be found just below the liquid surface. When working with BMG LabTech readers, you can select between manual or automatic focal adjustment, as shown here in this little screenshot on the left. The best focal height can be identified by comparing signal to blank ratios or signal intensities at different heights of your well. The automatic focal adjustment will do this for you and set your focal height to the peak of the generated curve. The software will even display the focal curve to you. In the scenario displayed in the graph here on the right, the optimal focal height would be 9 millimeters. And the graph also makes it clear that even a slight deviation from the optimal focal height can lead to a significant reduction in the signal to blank ratio, depending on the assay, of course, but this applies in both directions, with too low or too high focal heights. Focal height should always be adjusted on the brightest sample in order to obtain robust data for the generation of the focal curve. And although automatic focal adjustment reliably does this job for you, you still have to make sure to use the same sample volume in all wells of your plate. Otherwise, the optimal focal heights may vary from well to well. All measurements per well are done in the center of the well at one single measurement point. This is sufficient for most cases, especially when you're working with homogeneous liquid samples. However, it is a different story when working with heterogeneous samples, such as the adherent cells we were talking about. The graph at the lower right shows the signal distribution in a sample in a well, including adherent fluorescent cells, where red represents high signal intensities and blue and also pink represents low signal intensities. When looking at the distribution of signals in this well, it can hardly be denied that a simple measurement in the center of the well would not be sufficient in this case to adequately represent all cells and their signal intensities in the well. For such samples, we offer scan options. Here, the several measurement points are used on the surface of the microplate well and are eventually averaged after the measurement. Besides, for adherent cells, these scan options are especially of relevance for aggregation assays and also for microbial growth assays. We offer either orbital averaging, spiral averaging, or matrix scan. The matrix scan even allows to remove individual data points or whole areas of the well after the measurement has been done. This graph here on the right shows the percent CV over several replicate wells measured with different scan options. Percent CV is the coefficient of variance and describes data variability. As you want to obtain reliable and robust data from each of your replicates, a low percent CV is of course desirable. And as you can tell from this graph showing the percent CV of wells including fluorescent cell samples, scan options, of course, help to reduce data variability here substantially. In this example, the matrix scan at the very right delivered the lowest percent CV, followed by spiral averaging and orbital averaging. The simple measurement in the well center delivers the highest percent CV, and with this, the worst result. With all the advantages, it must of course be taken into account that multiple measurements during scanning and of course also the movements that are associated with it take more time. So it is therefore always necessary to balance accuracy and time expenditure. So much for me. Martin will now continue with other important parameters such as gain and flash number.
Thank you, Anne. Yeah, and with this, we are at I have just arrived at the point before starting the measurement. Still, there are some parameters left that can be optimized for best measurement results. One important parameter is the gain setting. The gain is a factor that defines the amplification of an incoming light signal by the microplate reader's detection system and influences the measurement range of a microplate reader. This is highlighted in the graph to the upper right. Simply put, a high gain will amplify the incoming signal to a greater extent and is thus suitable for samples with low signal intensities, while a low gain will amplify the incoming signal to a lower extent. Thus, it is very important to set your gain appropriately depending on your samples. To highlight this, we measured a fluorophore standard curve using different gain values. The results can be seen in the lower graph. The optimal gain value after gain adjustment was, in this case, 589. This is indicated by the yellow curve in the graph. For further measurements, we now selected 2 additional gain values above and 2 below this optimum to show the effects on measurement results. Here we plotted the measurement values over sample concentration. As you can see, a gain that is set too high will result in signal saturation, since the incoming signal is amplified too much and can't be depicted by the reader anymore. On the other hand, if the gain is set too low, samples with low signal intensities might not be amplified enough and might not be distinguishable from the measurement background anymore. So which gain should to optimize the gain setting, it is typically adjusted on the brightest sample on a microplate, same as the focal height. Using the optimal gain resulted in the best signal to blank ratio, as you can see in the graph to the upper right. To show this, again, we calculated the signal to blank ratios of a single fluorophore standard that was measured using different gains. Again, the optimal gain value was 589, and additional gain values below and above the optimum were chosen. Here we plotted the signal to blank ratio against the used gain values. Gain values that were too low or too high resulted in a reduction of signal to blank ratio further and further, as you can see. Naturally, this also has an impact on the achievable limit of detection. This is highlighted in the below figure. The lowest and best limit of detection was reached using the optimal gain of 589, while even small variations from the optimal gain impacted the limit of detection negatively. Another parameter can be taken into consideration when optimizing a measurement is the number of flashes setting. To give you a short explanation how the number of flashes settings work, with each flash, the sample is illuminated and measured once. Conclusively, when using multiple flashes, an average is formed from the separate measurements. This helps to reduce the effect of outliers, which can naturally occur in the measurement process. An appropriate number of flashes ensures accurate and reliable data. So in general, data variability is reduced increasing number of flashes. This is highlighted by the figure in the upper right portion of the slide. To show this, we again measured multiple fluorophore standards ranging from concentrations of 1 to 0.001 nanomolar using different flash numbers. Flash numbers are put on the x-axis here. Data variability in %CV were plotted against this number of flashes. While 1 and 0.1 nanomolar samples had low variability, even when using only one flash, this is in the left part of the graph, the increase of number of flashes significantly increased significantly decreased, the percent CV. While 1 and 0.1 nanomolar samples had low variability, even when using one flash, variability was significantly increased for low concentration and blank samples. Here, an increase in the number of flashes resulted in a decrease in variability. For most assays, 10 to 20 flashes are sufficient to achieve good results, which is also the case here. In this example, this gave variability values between 2 and 3%, even for blank and low concentration samples, which are the gray and light pink columns. In using more than 20 flashes only resulted in minor improvements of variability. Measurement time is also affected by number of flashes. With more flashes, the measurement time increases accordingly. So as before, with the number of scan points in a measurement, this should be taken into account when planning your measurement and to check or to weigh the measurement time versus the overall data stability. As a final parameter for measurement optimization, I would like to highlight the integration time. This parameter is mainly important in luminescence detection, but also in time-resolved fluorescence measurements. The integration time defines the time window that a microplate reader uses to collect light signals from a sample. Longer integration time can be used to benefit assays with a low photon yield over time, while short integration times can be used for assays with high photon yields. We have two examples here on the right. So we are first looking at the effect on luminescence measurements. In luminescence-based detection, the appropriate integration time is often determined by the assay type. On one hand, we have flash luminescence, which is the upper right graph, which shows a very fast decay of emission signals with high signal intensities shortly after the luminescence reaction. Accordingly, a short integration time is required here. Glow luminescence, on the other hand, which is depicted in the lower right graph, is defined by a slower emission decay, but low photon yields in comparison to flash luminescence. And accordingly, longer integration times are beneficial. With increased integration time, the measured emission signal will also increase, as more photons can reach the detector. This is useful since the signal of the sample may increase more than the signal from the assay background, as it's highlighted in the lower right graph. Furthermore, the longer integration time also has a beneficial effect on the data quality of glow type assays. Data variability, here again depicted in percent CV in the upper right graph, is reduced with increasing integration times. This is especially the case for samples with low signal strength. This is the light purple curve. On the other hand, the assay quality of glow luminescence assays indicated by Z prime and depicted here in the lower right graph also increases with longer integration times. Again, the low signal samples, you see a stronger effect here. However, please keep in mind that the advantages of longer integration times must always be weighed against the required measuring time, which is increased accordingly. But the integration time is not only useful in glow luminescence measurements. As you can see in the graph to the upper right, time-resolved fluorescence measurement assays use this setting to measure emission signals after background signals have subsided. Here the background signal is indicated by the gray curve. And this can lead to improvement of the signal to background ratio. This is true for both time-resolved or TRF, as well as time-resolved first resonance energy transfer or TRFRET measurements. Whereas TF-RED assays differ a little bit from TRF, since here we measure two emission wavelengths. And here, in this case, the donor fluorophore emits light upon excitation by the reader, while the acceptor only emits light when it is excited by the donor fluorophore upon excitation. But yeah, especially in the case of TRF and TF-RED, there's also a limitation to the usefulness of integration times. We have this highlighted here in these two figures. So for TF-RED measurements, the assay window can decrease with longer integration times. This is depicted in the upper right graph, even though data quality is improved, as indicated in the lower right graph by the Z prime value. This highlights that for TF-RED and TRF assays, longer integration times are not necessarily beneficial, and a balance in regards to the assay window and data quality have to be kept. We want to conclude today's presentation with a short summary of the most important points for optimizing microplate reader measurements. When planning a measurement, choose the appropriate microplate color. Check if your assay system is influenced by autofluorescence, adjust assay components where needed, and use bottom optics where required. Also optimize bandwidths and wavelengths to achieve best results. Before starting a measurement, make sure that the optimal gain is set to perform an adjustment. Make sure that the focal height is optimized properly and use scan options whenever you have a heterogeneous signal distribution over the well. Keep in mind that in most cases 10 to 20 flashes are sufficient, and that dependent on the application, longer integration times can be used to reduce data variability and increase data quality. And lastly, use scan options whenever you have a heterogeneous signal distribution in the well, and keep in mind that longer integration times reduce and increase data quality in luminescence, while integration times for TRF and TF-RED have to be optimized more closely for optimal assay window and data quality. And with this, we are at the end of our talk. Thank you very much for listening. And now let's switch over to our Q&A session.
Okay, thanks again, Martin, for summarizing the key messages from today's webinar. Now let's open the floor to questions. And as far as I can see it, a few questions have already been collected here in the meantime. But first of all, 2 notes in advance. First, the webinar will be available next week online on our website, and all attendees that were here present will be notified via email. And on a second note, due to, as I see many questions that have arrived here, I don't think we will be able to answer all of the questions during the remaining minutes here, but all the questions that can't be answered right now and that we can't cover right now will be answered in written format later on after the webinar. Okay, but let's start with the first question. What is the lower detection volume for microplate readers per well? Yeah, I don't think there's a general answer to this one. This clearly depends on the plate format that you're using. This definitely depends on the reagent that you use, so the fluorophore, luminophore, chromophore that you want to measure. And it also depends on the microplate reader, of course, of the sensitivity of the microplate reader. So should you be interested in more details on the lower detection limit for different readers, you can always visit our website where the specifications of the microplate readers we offer are presented.
Right. Maybe I continue with the next question. What is the best way to optimize integration start time for TRF-based assays using Aclarista Plus? Yeah, as I showed earlier, for the optical settings regarding wavelength and bandwidth, usually it is beneficial to keep a distance of around 30 nanometers to 40 nanometers between excitation and emission. And normally this should be yeah, perfectly sufficient here. So no need to go as far as possible, right, to separate excitation and emission.
Okay, unfortunately, it's not possible to have my video here at the moment, but I'm still continuing to answer another question. Let me check. There was another one on the use of quartz or glass plates. So the question is, I know there are also plates with glass or quartz bottom. Would you recommend these for the use with bottom optics? And in general, we can of course say that glass or quartz bottom is always a good choice when measuring with bottom optics, as the transmission through glass or quartz is of course very high. So the chance of signal being lost on the way is simply reduced. Further, glass and quartz show high transmission rates also over the whole detection range from 220 to 1000 nanometers, similar to cycloolefin that we have discussed before. So saying it's also suitable for the UV range. However, considering that especially quartz plates are very expensive, it must always be weighed up as to whether the additional financial expense is worth, or whether plates made out of polystyrene or cycloolefin would also do it as well.
Okay, maybe I address the question before. As I saw, I skipped one actually, or actually the answer was meant for the next question on the list. So again, for what is the best way to optimize integration time and for TF-based assays? So this will highly depend on the assay, of course. Usually you have recommendations provided by the kit manufacturer. So yeah, actually my first go-to recommendation is to use these presets where available. If you don't have presets available, the settings that are preset on the reader should be quite sufficient here. In the case you want still to optimize your measurements further, I would go from these presets and step by step change the integration time in subsequent measurements, and then yeah, calculate a parameter for assay optimization, such as the limit of detection, the LOD, and yeah, see if you have improvement by changing step by step the integration time until you reach an optimum.
Okay, next question. There was one saying, if the luminescence signal is too high, close to the limit of detection in a white plate, can we use black plates to have a lower signal? And the answer is, of course, yes. If you use a black plate, the signal will definitely be lowered, but this could actually be too much since, yeah, as we mentioned before, luminescent measurements depend on the signal amplification effect of white plates. And yeah, I would rather fear that the signal is then too low in black plates. So what I would rather do is start at the gain optimization point, reduce the gain, or maybe perform a gain adjustment with the features that we have in our software. And that's the go-to to reduce the signal intensity in luminescence measurements then.
Okay. So next question I got is autofluorescence in the blue and green wavelength range, I guess, still an issue in TRF-based assays? Yeah, as you might have seen in the slides, for TRF assays, we have a delay between the excitation and the actual emission of the measurement. This also means that you can set the detection of the emission signal so that the background signal is yeah, mostly declined, or in best case, fully declined. So to answer these questions for TRF-based assays, yeah, usually autofluorescence should not be an issue due to this reason.
Okay, another question, or maybe I can try to cover two questions with one answer, as one of the questions was for a 1 hour fluorescent measurement at 37 degrees, is it okay to cover the blade with a saran wrap to prevent evaporation? And then there's also another question, directing to a similar topic. Let me see if you can find. Yeah. Is it better to take OD measurements with the plate lid on, or do you need to remove the plate lid before taking reading? So general answer to this one is it is of course always better to do the measurements without a lid or a plate cover or a sealer or a wrap on. The addition of something in the light path just has a risk to maybe reduce the signal, for example, for fluorescence measurements, or it could also add some background to some measurements. So a measurement without, if possible, is always better. We are, of course, aware that there are some measurements where it is simply impossible to measure with nothing else in the light path, so no cover, no lid, no anything. For example, if you measure in a kinetic setup over some time, if you have cells in your plate that have to stay sterile, in those cases, you just need something that covers the plate. For these occasions, we usually recommend plate sealers, which are especially developed for such experiments and which usually have a low background and a high transmission rate, but do the job to cover your cells and to keep them sterile or avoid also evaporation in experiments.
Okay, next one. Fluorescence background from white plates will be strongest in a filter-based plate reader. How big is the background effect with a monochromator-based system, double monochromator-based system? Yeah, so to answer here, in general, the background signal should not be highly related to the choice of filter or monochromator, but this is probably mostly due to the choice of microplate color here. So actually, my recommendation would be to switch to to go away from the white plate, since with white plates you have higher signal amplification due to reflection. So my recommendation would be to change white plates for black plates ideally, or to clear plates if you don't have a black plate available.
Okay, another question to be answered by me. If automatic gain adjustment is used, does the brightest sample need to be defined, or will the plate reader scan for the brightest sample? Well, that's easy because in the end it's up to you. We have just talked about that for the gain adjustment, or also the focus adjustment, the sample with the brightest signal to be expected should be selected. And if you are aware which sample in your whole plate, which will deliver the highest value, you can simply select it and then do the automatic adjustments on that well. If you're not completely sure which one will deliver the brightest signal, or if you forgot about your plate layout or something like that, you could also use an automatic function of our software where you pre-select all wells of your microplate and then select the automatic gain adjustment. And this way, the reader will do the job for you. It will actually identify the well with the brightest signal and perform all the adjustments on this very well.
Okay, next question for me. So, will excessive plate shaking cause damage to the plate readers? Was upvoted by a few people. So, let me maybe rephrase. So, in general, no. If you have measurements with very high intensity, so we are speaking about 700 RPM and above, and over a long time, so multiple hours to days, then there can be the possibility that either the plate could detach, or there's some plastic dust generating from friction during the shaking. But in these cases, so if you have high intensity shaking applications, we offer a special shaking plate carrier, so our long-term shaking plate carrier. And this can be equipped on the reader, so the reader can be upgraded with this. This plate carrier is actually especially designed for these long-term shaking applications that shake over multiple days. So with this option, you are perfectly covered in this area. And maybe I also add another question from the beginning, since I moved this up a little bit. So in terms of bandwidth for fluorescence, is it recommended to shift bandwidth as far right as possible to reduce background signal? So here the answer is that 30 nanometers between excitation and emission should be perfectly fine. So there should be no need to move further right to the for the selection here.
Okay, another question here. What does it mean when all wells indicate overflow when measuring fluorescence? So overflow means nothing less that the signal is in the range of saturation, so that the reader is not able to differentiate anymore between individual signal intensities, since all of them are over the top of the possible signal detection range. In practical aspect, that means that your gain is set too high, so you would have to reduce the gain. If you have the possibility, you could either do a measurement with enhanced dynamic range, which is available on our Vantastar, the Clariostar, and the Ferrastar FSX, or you could do another automatic gain adjustment. This is especially important and maybe a little bit more difficult if a kinetic setting is used, where your signal maybe develops over time from a low signal at the beginning to a high signal at the end. For such scenarios, we usually recommend to start with a target value for the gain adjustment of not more than 10%. Maybe this could help to overcome this.
Okay, and now our time slot is actually closing soon. So I would like to thank every one of you for attending the webinar. As Anne-Catherine mentioned earlier, all open questions will be answered via email. So we will contact you and give you an answer there. And also you will receive a recording of the webinar probably early next week. And with this, let me say thank you again. Thank you for attending, and see you on the next webinar.